Hello. Now I am going to describe how to derive the variance of a two-step estimator. So first of all, I'm going to define the derivatives. So the basic structure of the derivation is quite similar to what we did in the previous chapter, chapter 3 and chapter 4. So the Taylor expansion, and we show that a certain term goes to a constant and which is invariable, and another term goes to normal distribution by the central limit theorem. And then by inverting, you can show that the estimator converges to something. And we are going to use the same rationale, but I will introduce a new concept, which is also very useful. So anyhow, first of all, I define the derivatives. So the derivatives are important because we are going to use the Taylor theorem. And under suitable assumptions, I'm not going to state the detailed assumptions. And remember, there are several assumptions like compactness and like continuity and supremum is bounded, blah blah blah. So those assumptions, under suitable assumptions, we could show that the first stage estimator follows this asymptotic distribution. So this is the result of Taylor expansion and like Slutsky theorem, central limit theorem, uniform convergence, and like blah blah blah. So what I'm going to show you here is, and we are going to apply, in the end, we are going to apply central limit theorem to this guy. But instead of doing that at this point, you may rewrite this as something like this: square root n times square root n, and it is a sample average of this guy. So sample average of this multiplied by square root n, and we will write this part as phi I. So this is a function minus large M inverse small m I gamma 0 will be simplified to psi like phi I gamma 0. So phi I will be called the influence function, and as you can expect, we are going to apply the central limit theorem for this guy. So by simply applying the central limit theorem for this guy, we have the normality for this one. But now I'm not going to show you the final variance, because our goal is to show the asymptotic distribution of theta, not gamma itself. So I will just stop here. I will stop here, not applying the central limit theorem. And this influence function will be very useful and very convenient to study the second stage estimator, because this function contains all the information relevant to the first stage error, right? So remember, what we just did is, this is square root n times estimation error can be written as approximately square root n times sample average of a certain function. So the estimation error is approximately the sample average of this guy. So, and we may interpret this phi I as the ith observation's contribution to the estimation error, right? So it depends only on the ith observation and gamma. So it is very useful information to study the estimation error from the first stage estimator. So we are going to now, let's consider what happens to the second stage. So first stage is standard. It is exactly the same as what we did in chapter 3, but in the second stage, it's slightly different. The reason is, we have two arguments. The moment function has theta and gamma as its arguments, And of course, we are going to Taylor approximate this moment function by a linear function of theta and gamma at the same time. So you have to differentiate this function with respect to theta and gamma at the same time. So the mean value, intermediate value, is theta bar, gamma bar. So then look at this. 0, the first order condition equals to this, and like this, if you linearize, linear approximation of this function can be written as theta 0, gamma 0 plus difference in theta hat and theta 0, and difference in gamma hat and gamma 0. Now, structure is pretty much the same as before. We consider AN, BN, CN. There are 3 terms. We just need to show how they behave. But another thing you have to keep in mind is we are only interested in this guy. So theta hat minus theta 0 is what we want, but gamma hat minus gamma 0 is not what we want. So we are not interested in gamma 0. And also, actually, gamma hat minus gamma 0 is already known. We derived its asymptotic distribution like this. So this part will be treated differently. We are going to plug this result into this part. That's why we defined the influence function. So then, like, it is known, so it is not a big problem. We want to know this. We need this part. And AN, BN, CN, we know how to handle them. And gamma hat minus gamma 0 is known. So in principle, you know everything. So you can just rearrange. So let's see. If you rearrange, what we need is square root n times theta hat minus theta 0. And simple math gives you minus bn inverse and square root n an cn gamma hat minus gamma 0. And under the assumptions that we studied earlier, I am not going to go in detail about the assumptions. Anyhow, under those assumptions, you can show that this will converge to a matrix inverse, constant matrix inverse. So Bn will converge to this guy. We already defined the derivatives, expectations of derivatives here. So using these guys, you can show that Bn inverse goes to something, Cn goes to something, and then as a result, this is what we have. And so this part can be written as an was this part an will be approximately this. So g hat will be very close to g, and this part will be approximately this, right? Gamma hat minus gamma 0 is replaced by the influence function, and the derivative converges to this guy. So there is and this requires uniform convergence. So this is what we have, and also you may simplify them again, gi and phi. So combine them, and g gamma is here. So you can bundle them into sample average. The reason why we write this way is because in the end we are going to apply the center limit theorem. So we need to have square root n times sample average. So we have a nice form. This is why we need phi. Phi, by defining phi, you can simplify the notation a lot. And then continue. Then the final result is Bn inverse is replaced by g theta inverse, and apply center limit theorem here. by the center limit theorem, first thing you need to show here is that the expected value of this is 0. So minus 0 is hidden. So the original center limit theorem is square root n times sample average minus population expectation. But population expectation is not required here because it is 0. You can show this by yourself. Like, remember, it's about moment condition. And then apply the center limit theorem. Then you have this center limit theorem, this form where omega is the variance of this, right? The variance of this is the variance of this center limit theorem. So as you see, the rationale is pretty much the same. I just did not fill the gap. You just need to state like what's the required assumptions, like what's the required assumptions for the uniform convergence center limit theorem, or like a Szulowski theorem, continuous mapping theorem, and Taylor expansion, blah blah blah. So in the end, we have this. So, and then this variance can be also written as this times this prime. So also the same as before. Therefore, in the end, watch this, g theta inverse times something like normal, approximately normal with variance omega. So the whole asymptotic variance of the estimator is g theta inverse omega g theta inverse. Prime is hidden because g theta maybe actually had to be primed, so transposed. So if g theta is symmetric, then you can write it this way. Okay, so like if you cannot follow, please compare what we are doing now with what we have done in chapter 3 or chapter 4. So, and later soon I'm going to give you the application to two-stage least squares, the instrumental variable regression model. So then I think you can see it more clearly. Several comments related to that. So we have, this can be understood as the second stage influence function. Observe this. This is estimation error. Estimation error can be written as sample average of, if you bring g theta inverse inside, sample average of this guy, right? So again, this can be interpreted as the ith observation's contribution to the estimation error, right? So you may interpret this as the influence function for this. And among here, this much is the error, the estimation error from the first stage, and the estimation error from the first stage is multiplied by g gamma and g theta inverse, and so in the end, this much is the contribution of the first stage estimation error. So if you do not consider the first stage estimation error, then you are treating this equals to 0. If you ignore the first stage estimation error, you will have this equals to 0. So your standard error may be smaller or can be larger. So anyhow, your standard error will be wrong. So that is the major problem. And observe this. So if you ignore this part, then the final asymptotic variance is exactly the one-step M estimation asymptotic variance, which is wrong. So you have to know that that is wrong. You cannot use the same formula in two-stage case. That is the most important lesson you have to understand here. And so this is the idea. So variance of G and first stage error. So G is the moment function for the second stage estimation, and this much is the contribution from the first stage estimation error. And if you think about its variance, you can write this as, so if we assume everything is scalar, if everything was one-dimensional, you can write this variance as variance of this plus variance of this plus 2 times covariance of this, right, between them. And then the problem here is if there is no covariance, if there was no covariance, the first stage error will increase the variance because this is always positive. So the here G gamma should be multiplied. Excuse me, that's typo. Anyhow, if you ignore the covariance, this is always positive. However, the covariance may be negative. Possibly covariance can be negative, and in that case, if it's very negative, then this additional term can be negative. So this variance is when you ignore the first stage error, but because of the first stage estimation error, you have this much in addition to the variance in the moment. But the additional term, in theory, can be negative when covariance is negative. And that happens in the two-stage least squares. So we will see how this can be a negative term. So it is very interesting. Like exactly that's what I'm explaining here. And sometimes the first stage estimator may not have any impact on the second stage, which is also very rare. So sometimes it is also true. So standard errors may not does not depend on the first stage estimator. In this case, in theory, the G gamma is 0. The derivative with respect to gamma is 0. That's why the first stage estimation error has no effect on the second stage. And this is a nice result because you are dividing the first stage and second stage estimation to make the computation easier, and but the cost is a more complicated asymptotic variance. But if the first stage error does not change your second stage error, standard error, then you only gain the computational advantage, but you are not paying anything. And this happens, and Newey and McFadden explains it very well. This is a typical example of this example is the optimal weighting matrix. Optimal weighting matrix, when we calculate the optimal weighting matrix, I remember, so how you two-stage optimal weighting matrix GMM. When you do that, in the first stage, you may choose any weighting matrix and estimate get any consistent parameter. So, and then using the first stage estimator, you calculate the variance of the moments, and then using the optimal weighting matrix, you obtain the efficient GMM estimator. And we learned how to calculate the variance matrix of the efficient estimator. But you need now think about this. I said you may choose any weighting matrix at the beginning. No matter what weighting matrix you choose in the first stage, second stage variance does not change, right? So second stage asymptotic variance does not depend on what is your first stage estimator. Theoretically, that happens, and this happens when your final estimator is consistent, even if your first stage estimator is inconsistent. So think about the optimal GMM concept. What we want here, so remember, no matter what weighting matrix you use, your GMM estimator will be consistent. Right? True. And second, the only reason we are using the optimal GMM matrix, optimal weighting matrix, is because we want to have a more efficient estimator, a smaller variance. So therefore, like even if but just to obtain a efficient estimator, you estimate a first stage estimator and use a better weighting matrix. But even if the weighting matrix is wrong, even if the weighting matrix you calculated is not optimal, still it is not a big problem because your estimator will be consistent no matter what the weighting matrix is. That's the So this is this is the condition when the first stage has no impact on the second stage standard error. So if your first stage does not affect your second stage consistency, then that means the first stage error has no effect on your second stage variance, which is very interesting. So again, connect what I explained to the GMM example and think if it makes sense or not. And now you will realize the GMM two-stage estimator is a very beautiful theory. So it has many nice and interesting, beautiful results. So now you can view the theory and understand it much better. Okay, it's too long, and I will continue to the example in the next one. So thanks.